Welcome. Today I'm going to talk to you about tangential velocity. This makes up the topic for video 34A. So I've split 34 into two parts because I think it's a little more easy to handle each topic individually. This topic is tangential velocity, but it's based on the idea that the type of motion we talked about in the last couple of weeks is actually different than what we're going to be talking about now. And so I want to draw that distinction before we get too far into it here. So first and foremost, what we've been talking about over the last 2 weeks has been rotation. Rotation is motion around an internal axis, some point around which an object is spinning. Let's take, for example, the Earth. The Earth rotates on its axis. And so I've tried to draw the Earth here rotating on its axis. The axis is, of course, angled. That's why we have seasons. If you don't know what I'm talking about, come and talk to me because it's important you understand that. Anyway, let's imagine the sun is over here on the left, and the sunlight is hitting this side, but the side is in shadow, and so as the Earth spins through the sunlight and the darkness, we end up with a full day, which is just about 24 hours in length. Almost exactly 24 hours in length. So you can see that the Earth and the motion and the parts of the Earth, if you look at it, are all moving around this internal axis right here. What happens though if I take that axis and I put it someplace else, someplace outside of the object? Well, we end up with something more like this, where if we imagine now the Earth is now moving in a circular path around another object. Let's say that object is the sun. And so we have the sun here at the center of the solar system, and the Earth is moving around it. We can't really call that rotation anymore because the axis is not internal. It has to be external. The sun is way far away from where the Earth is, and so it has a new name, and that new name is what we like to call revolution. So we say the Earth rotates on its axis and also revolves around the sun. So there's the two technical ways to use those terms. A lot of adults will use those two interchangeably, and in physics that's not really, at least in astronomy, that's not really the way it is. Anyway, so now we're going to be talking about, for the next week, objects that move in a circular path around a point outside of themselves. So here, as we said, the Earth is moving around a point that is sort of in the sun here. And it's because of the force of gravity that it does so. We'll talk more about orbits when we get to gravitation later on. But lots and lots of different kinds of objects move like this. In fact, we have objects, let's say you're driving in a car. So just real quick, here's a car, an overhead view, and a car is riding along the road, and let's say the road goes like this. Like so. Okay. Now, if you just took your hands off the wheel and you took your feet off the pedals, your car would continue to coast in a straight line and go off in this direction, and you'd be sad off in the field in the snowbank probably. So you have to apply a force using the steering wheel to be able to get it to go in a circular path. And really that's what we're going to be talking about this week. Okay, so the reason why the car wants to move in a straight line at the same speed is because of this idea of inertia. And inertia goes all the way back to Newton's first law of motion. Remember, it's Newton's first, which was actually Galileo's, but that's okay. So there must be some force that's being applied to get it to go in a circular path. And so that's the topic for the next video. This video, though, talks a little bit about how you can describe the motion as it goes around in a circle. Well, velocities, as you can see here, have to be in a straight line. And so we can talk about the velocity, but there's a problem because we know that it's not actually traveling in that straight line direction. And so we have to be able to apply some sort of acceleration to it to be able to explain how it works. Again, that's the topic for the next conversation. But for now, you could do it in two ways. So you could describe the motion here either by the angular velocity, and that would be like how many rotations per second is the object making. We did that for rotation. Now for us, For this new type of motion, we'd say revolutions per second. If you've ever played one of the old LP records, you know that those LP records are measured in revolutions per second, or excuse me, per minute. So 33 and a third is a common speed for some of those discs, the large discs, and that means 33 and a third RPM, or revolutions per minute. Now, that's okay to do that. You could also, so I'll write that down here, revs per second, or per minute if you want. Or you could remember that if this is the center point, and this is the object right here, that the radius sweeps out an angle as it goes across, and that angle, when it goes through a full circle, ends up being 2 pi. So you could do radians per second as well. So acceptable rate units for angular velocity as it talks about revolution. So you could do revs per second or rads per second. Either one would be fine. Remembering that there's 2 pi rads in a rev, if you want to think about it that way. There's 2 pi radians in one revolution. You could do it that way. But the other way to talk about it is just to talk about the tangential velocity. It's just like saying the speed, but then adding the direction. And the direction, because it's a vector, and because it takes into account Newton's first law, which is the law of inertia, it would be like what would happen if you took your hands off the steering wheel and just let the car coast. If you let the wheels snap back to the forward position, you know that your car is going to end up going straight instead of going around this turn. It's the same thing here. Let's say that I have an object and it's attached to a string, which I'm holding here at the center. And I'm twirling this object around, which is actually an activity we're going to do this week. If that string were to break, the object would fly off along the tangent to the circle, just like this, at the speed it was going when the string snapped. Why? Because of Newton's first law of motion, because objects move in a straight line at the same speed unless they're acted upon by an outside force. The outside force is applied by the string. Again, we're going to talk about that next time. But once that string is gone, that string force is gone, then the object is just going to move in a straight line at the same speed. We call that a tangential velocity because it's tangent to the circle. Tangent just means touching the circle in one point. Wouldn't you agree that this vector right here touches the circle in only one point? Tangential velocity is basically the exact same thing that your speedometer would read on your car as you were going around a corner, just also with adding in the information about which direction your car is pointing. So this is the way I like to think about it. It's not just which direction your car is pointing or the speedometer reading, but it's both together. Now there is a relationship between the angular velocity and the tangential velocity, and it's right here. But we're not really going to do a lot of math with that. It's just important for you to understand what the concept is here. We are going to do math with tangential velocity, so you're going to have to know a little bit about how to calculate it. And so there's just one last piece here. And you can see, since this is a circular path has a distance around that is based off of the circumference. And the circumference formula is 2 times pi times r. Or, if you wish, pi times d. Either one will work. That's totally fine. Typically we use this one because we oftentimes have radii and not diameters. So here's the question. If I know how long it takes to go around one revolution, and I know the distance it takes to go around, I can find the tangential velocity. And so for me, I like to write this like so, is equal to the 2 times pi times r over the time that it takes to go around. This is not on the formula sheet because it's really just logical. And I guess I kind of assumed that people would understand that. If you're moving in a circular path, the distance around the circular path is found by the circumference. If you're moving in a circular path and we want to find the speed, you have to be able to figure out the time that it takes to move in that path. And so therefore, if we can divide the number of meters around and the distance that you travel divided by the time that it takes to travel, you end up with the speed. And the speed is just the velocity with the extra added information of having that direction. And that direction is tangent to the circle. So we're going to use that in the next video. So hopefully that makes sense. If you have any further questions, please let me know. Thanks for watching.